When we first started to design this computer, we looked at our history, which was from personal computers. And we said, what is a PC architecture? Well, a PC architecture is you go get some memory, and you add to it some video and a CPU, and everything works fine. The problem is that when you decide that you want to go 10 times faster and put 10 times as many dots on the screen, the path to memory burns up, and you cannot get the information out fast enough. So PC architecture breaks. And we thought, what should we do? Well, we looked at workstations. And workstations put a cache on the CPU, and they put some dual-ported memory on the video, and it works. The problem is that's where they stop. Because if you look at a typical workstation, the minute you add a network, it starts to bog down the system enormously. And then you add fast disks. You might add some fast I/O in terms of a backplane or a bus. You might add something like audio. And for high-quality audio, like you find in a CD player, it demands quite a lot of data. So this can also start to pull your computer down. And you might want to put an attached processor, like a digital signal processor on your computer, and you've got to get a lot of information to it and back from it. And again, things just don't work. And so what we found was that this didn't work, and we had to invent something new. We asked ourselves, has anyone else done this yet? Maybe we're getting a little lazy as we get older, but rather than reinventing it ourselves, we looked around, and the answer was, of course, yes. Who solved this problem? Mainframes. This is exactly what mainframes have done for the last 25 years. And it may sound funny coming from us, but we decided to copy this architecture. And so what we did was we looked at how mainframes do it. What they do is they have I/O processors on every single I/O channel, as they call them. And then they have a very sophisticated memory system which doesn't let the processors into memory until they're ready to get in and very efficiently get out. And what that all adds up to is this. If you look at the overall system throughput of a computer, PCs have about 10 megabytes per second, workstations about 20, and mainframes about 40. And you can see some of the other parameters there. So what we wanted to do was make something more like a mainframe. But rather than making something like this, which is how the mainframes typically do it, we decided to build a VLSI group, and we put a mainframe architecture on 2 VLSI chips. It took us 3 years to do this, but the performance is staggering. We are within striking distance of a mainframe. We have one board and about 45 integrated circuits. And this is the board right here. So this is our architecture. We actually use 3 processors, a Motorola 68030, floating point unit, and a new type of processor to computers, a digital signal processor, and we'll talk a little bit more about that later. And we have 12 I/O processors, each with their own direct channel to memory. And you can see what they're for the backplane, the serial ports, the printer, the DSP, the audio, the disks, etc. And we can be running all of these at one time and still only be chewing up about 1/3 of the overall system performance. Now, let's take a look at the sound hardware. We wanted to build in sound in this computer. And we thought to ourselves, when you pay thousands of dollars for a computer, why should you get less good sound than you get on a few $100 compact disc player? And the answer is, of course, you shouldn't. So we built in CD quality sound, built in high-quality digital to analog converters, and we also built in this new thing called a digital signal processor. And a digital signal processor is a processor that's optimized for processing certain types of algorithms about up to 100 times faster than the main CPU. And this is useful for things like sound, music, and speech, which we'll hear some of today, faxes, image processing, all sorts of other types of things. And there's one built into every next computer. Now, why did we build it in? Like many things we built into the computer, we discovered in talking with software vendors that if it takes an additional plug-in board that cost a few $1,000s with a DSP on it, they won't use it in their software because they won't sell very many pieces of their software. They'll only use it pervasively if it's built into every computer. And what they told us is if you want to make a revolution, raise the lowest common denominator, and you'll see the revolution happen in the software. And that's what we did. And this is our lowest common denominator. That's the board. These are the two mainframe on a chips here, processors, custom video, all the networking built in. We'll go through some of this other stuff a little bit later. Okay. Most of you have probably seen pictures of the NeXT computer. I thought I'd run through a few. This is what it looks like. It's in a 1-foot cube. And this is the back of it. We have one board that is the whole computer, as we just saw. We have slots for 3 additional boards. We have the power supply here that plugs in anywhere in the world. You find the power cord, it works. This is what the inside looks like. Very easy to service. We have room for 2 full-size 5¼ Winchester drives inside so that we can put over 1 gigabyte of storage inside this 1-foot cube. This is what the display looks like. It's on a stand. It tilts very easily. And the back of it, again, has a connector to go to the cube, connector for the keyboard, connector for an external microphone, and it has a speaker built in down below, but it also has a stereo Walkman headphone jack and gold-plated line output jacks to go to your stereo. It connects to the cube. Well, wait till you hear the sound it makes. It connects to the cube with one 3-meter cable here, and that 3-meter cable supplies it video at 100 megahertz. It also supplies it power. So because this works anywhere in the world, this also works anywhere in the world. It supplies it with digital sound, which is converted to analog in the monitor. It takes back the keyboard and mouse data to the cube, and it also takes back the digital microphone data to the cube. So it does its work. And this is our laser printer. It's a very interesting laser printer in that it's a price breakthrough. It also is 400 dots per inch, which is about 75% greater aerial resolution than 300 dots per inch. And it's a full PostScript output. So truly what you see is what you get. Now, let's get to software. We went out and asked software developers, what would be a revolution? We're designing this new computer. What do you want to see? And it was almost unanimous what they wanted. What they told us was, before Macintosh, the world was simple. It had agreed on a user interface of 80 by 24 characters. And when you wrote a program, you wrote the guts, and that was it. But all of a sudden, Macintosh comes along, and Macintosh was a revolution for the end user, but the developer paid the price, unfortunately. And so what used to be 100% of the guts is now only half the code, and they told us that the other half of the code is this user interface gobbledygook. But it's worse, they said. They told us that in many cases the guts is already lying around in C somewhere, that that's not where their time is, that 90% of their time is in the user interface, and that if we wanted to make a revolution, to attack that. And we did. What we did was we took that 90% pre-NeXT, and we reduced it by almost an order of magnitude by creating something we call an application kit. Full object-oriented programming and a very large body of code that has many objects that every developer will need to build their application, done precisely, done for them. And that got it down to about 10%. But then we went further. We wrote a program that runs on top of the application kit called Interface Builder. Oh, forgot. This is why the application kit works. In a Macintosh, which I love, there are about 400 procedure calls to do the user interface. And if you're an expert over time, you get very good at knowing what they are. We've replaced this. It's actually up to about 25 objects now. That's all you have to know to program this system. And we'll go through a little bit. But we reduced it even further. This program called Interface Builder lets us graphically lay out the user interface and connect things with lines. And we can actually get the time to build a user interface down to close to 0. And we have gotten unanimous feedback from the software developers that this is revolutionary. This is what our software architecture looks like. We use a version of Unix called Mach, which is 100% compatible with BSD Unix. We use PostScript from Adobe, and this is PostScript on the screen as well as the printer. We worked with Adobe to define what's called Display PostScript, which works very, very fast on the screen, as you'll see. Everything on our screen is in full PostScript. And then we have these 4 layers, the Windows Server, the App Kit, Interface Builder, and the Workspace Manager. And together, we call them, these 4 layers, Next Step. So when you hear that term, that's what it means. And an interesting thing happened. One day, another computer company came and knocked at our door. And they said, we heard you're doing something pretty revolutionary and we'd like to see it. So we got all of our stuff and we flew back east and showed it to John Akers, because we figured he's not going to run back and program it. And they liked it so much they licensed it from us. And so we actually licensed Next Step to IBM. And what's so interesting about this is that you can develop an application for either platform and nothing underneath the green matters. You can recompile it in a day or 2 to be running on the other platform with the same user interface, the same training, and the same documentation. In a day or 2. These are some of the companies developing applications for Next. We'll have about 100 applications out by the end of this year. And what I'd like to do now is take a few minutes and answer a few questions that we get asked all the time that are important questions. There's